Okay, I wanted to start back at example 8 from the beginning, just to make sure we've gone through every step of how to graph a rational function. So the first thing we're going to do is find the y-intercept, and to do that, you plug in 0 for x, and for that, you're going to get -3/2, and that's going to be right there on your graph. Now you're going to find your x-intercepts, which is when you set the function equal to 0, and that is going to be just x equals -3, because that's the only way to make that equal 0. So that's going to be right there where it crosses the x-axis. And then find the vertical asymptotes. That is where the denominator will be 0, and that's going to happen when x is equal to 2. And so we will put that vertical line, x equals 2. The horizontal asymptote, remember, is you look at the numerator and denominator of your function and see what is going to dominate. The numerator and denominator have the same degree. They're both linear, and so x to the first power. And so neither the numerator nor the denominator is going to dominate. The leading term on top and bottom will dominate, and those are x and x. So this, the horizontal asymptote is just going to be x over x, or 1, y equals 1. So that will happen right there. So those are our asymptotes. There is no slant asymptote because the numerator has to have a degree 1 greater than the denominator for that to happen. So that's not going to happen. So now we're just going to see, does the graph cross the horizontal asymptote? Because remember, it can do that. And the way to check that is, because our horizontal asymptote is y equals 1, we're going to see if the function can equal 1. So x plus 3 over x minus 2 equals 1. See if you can do that. Just try to solve for x, and you will have x plus 3 equals x minus 2, which says 3 equals -2. That is not possible. So no, this graph cannot touch that horizontal asymptote. It can't cross it. It can't touch it. Okay, so at this point, you've got to figure out where the curve goes. The book checks for symmetry, but I don't think that really does much for you, because you can already kind of tell it's not going to be symmetric because of where the asymptotes are. So when I started showing you this in class, I went through different intervals on the x-axis. Sometimes you need to do that. Sometimes you don't. Sometimes it's obvious where this graph is going to be. And in this case, it's it is obvious, because you know that as you go from negative infinity up to -3 on the x-axis, you know that all the way to infinity, it's got to be approaching that asymptote. So it's got to be coming like this, and then you know it's going to cross the x-axis at that 0. So just remember, whatever the graph is going to look like, it's always going to be approaching the asymptotes. And then you know, since you just reached a 0 on the x-axis, the graph is going to cross the x-axis, and it's got to go through the y-intercept, and then it's got to approach that vertical asymptote. So there's no other way for it to look in that region. So we just checked the whole region from negative infinity up to +2 on the x-axis. All right. Now we need to check what the function is doing on the x-axis from 2 to infinity. The question is it above, is it up here, or is it down here? And all we have to do is check one point to find out where the function is, because if it's up here, it can't get out. It's trapped in between those two asymptotes. If it's down here, it's going to be trapped down there. So one point will tell us the whole story. So we can just pick a value on the x-axis in that part of the graph and see what we get for y. So f of 3, we'll use 3. So f of 3 is going to be 6 over 1. So the point 3, 6 is on this graph. So you can see that from 2 to infinity, this graph is going to be up there inside that square where that point is. And so the only thing it can possibly do is to approach the asymptotes. And so it's got to look like that. There's no other way to draw it so that it will approach the asymptotes as x gets infinitely large and as x approaches 2 from the right. 4x over x squared minus 4, we're going to find the y-intercept. So that's f of 0, and that equals 0 over -4, and that is 0. So this function has its y-intercept at the origin, 0, 0. The x-intercept is when the function equals 0. So 4x over x squared minus 4 equals 0. The only way that can happen is if x is 0. All right, vertical asymptote. You're looking for the x values that will make the denominator 0. So x squared minus 4 equals 0 gives you x is plus or minus 2. So there are two zeros, two vertical asymptotes right there at 2 and -2. X equals 2 and x equals -2. All right, so we've got our vertical asymptotes. Now we're going to look for horizontal asymptote. The degree of the numerator is less than the degree of the denominator, which means that denominator is going to dominate. Therefore, the function approaches 0, and the asymptote is the line y equals 0, which is the x-axis. Now, the question of whether it crosses or not, I'm saying it does cross, and we know that because the function can equal 0. If you set 4x over x squared minus 4 equal to 0, we already know that happens when x equals 0. So it does cross. So next, we are going to see if there's a slant asymptote. The degree of the numerator is not one more than the denominator, so there's not going to be a slant asymptote. Then if we look at symmetry, this function is an odd function since f of negative x is equal to negative f of x. So it is symmetric about the origin. We have to look at the different regions that we've got here. We've got a lot of rectangles here, and we need to know, where is the curve? Is it above the horizontal asymptote, below the horizontal asymptote? From -2 down on your x-axis, we're just going to check a point in that region. So I'll try -3 on the x-axis. So f of -3 is going to be -12 over 9 minus 4, which is 5. So -12 fifths. So we're talking about this point, -3, -12 fifths. So in that region on the x-axis from -infinity up to -2, your points are going to be below that horizontal asymptote. They're going to be, the value of the function is going to be negative. It's got to approach the asymptotes, so it's got to look like that. All right, now we need to check the next interval on our x-axis. It could look like this or this. It's got to go through that point, and it's got to cross the asymptote. So it's going to be one way or another like that. So we just need to figure out where is it positive and where is the function negative in that region. So we'll just look at the region from -2 to 0 on the x-axis and see whether the function is positive or negative there. So from -2 to 0, any point in there, let's see what that's going to look like. So I'll pick -1. So f of -1 is going to be -4 over 1 minus 4, which is -3. So that's going to be positive 4/3. And so that tells me that the point -1 4/3 is on the graph, which means that from -2 to 0, this function is positive. And then if you look at f of 1, you're going to get a negative value. So f of 1 is going to be 4 over 1 minus 4 is -3. So you have a negative value there. And so there's that point. And so you know from 0 to 2 on your x-axis inside that little rectangle there, you're negative. So you're going down like that. You're approaching the asymptotes. All right. Now on the right side of 2, from 2 to infinity on our x-axis, we just have to find out, is it above or below the x-axis? And we know it's going to be above because we found out that it is symmetric about the origin, which means that it's going to have to be symmetric like this so that there's another curve like the one on the lower left up there on the upper right that looks just like it. So we do know that, but we can still check a point. So if we try f of 3 in our function, we're going to have 12 over 9 minus 4 is 5. So 12 fifths, and that's right there. So we know, and it is approaching the asymptotes. So it looks like that. Okay, so we're going to find that y-intercept. We'll just put in 0 for x and see what we get. So we'll have -5 over 1, which is -5. So the y-intercept is -5. So we graph that on our graph. Now we're going to get the x-intercept. We're setting the function equal to 0. And remember, the only way for this function to equal 0 is if the numerator equals 0, because the denominator can't equal 0 because that is not allowed. So we'll solve that quadratic. And it does factor, thankfully, and we get 2x minus 5 and x plus 1. So our x-intercepts are the zeros of the function, and that would be 5 halves and -1. So we will graph those 2 points. Now we're going to look for the vertical asymptote. The vertical asymptote is where the denominator is equal to 0, and this denominator cannot equal 0. The horizontal asymptote, if we look at the numerator and the denominator of this function, they have the same degree. They are both quadratic, and so you just look at the leading terms, 2x squared over x squared. Those are going to dominate the numerator and denominator. And so 2x squared over x squared, as x gets very large, that just approaches 2. In fact, it's always 2, whether x is large or small. So that is going to be our horizontal asymptote at y equals 2. And now we would check to see, does the graph cross that horizontal asymptote? And the only way it is going to cross it is if it can equal that. So we set it equal to 2 and cross multiply. So we're going to have 2x squared plus 2 is equal to 2x squared minus 3x minus 5. Cancel the 2x squareds, and you have 3x equals negative 7. So x equals negative 7/3. So this function does cross the horizontal asymptote when x is negative 7/3, right there. So for the symmetry on this one, g of negative x does not equal g of x, so it's not symmetric about the y-axis, and g of negative x does not equal the opposite of g of x, so it's not symmetric about the origin, so symmetry doesn't really do anything for us. Does it have a slant asymptote? No, because the degree of the numerator and denominator are the same, and that's not a situation where you would have a slant asymptote. All right, so we have to figure out what's going on here. Where do we draw the graph? Well, first of all, I would check the interval from negative infinity up to the place where it crosses that asymptote. So negative 7/3. I'm going to check values in that area just to make sure. I know there's really no other way to draw this except that it's going to be starting out above that asymptote because it's going to come and cross it. But just in case I'm not sure, I'm just going to check a value between negative infinity and negative 7/3 and see where the function is at that time. So I'm just going to check negative 3 since that's a whole number. So g of negative 3 is equal to 2 times 9 minus plus 9 minus 5 over negative 3 squared is 9 plus 1. So that is 18 plus 9 is 27 minus 5 is 22. So that's 22 over 10, which is about 2.2. So negative 3, 2.2 is on the graph. So yes, it is above the horizontal asymptote from negative infinity all the way until the point where it crosses that horizontal asymptote. So it's got to be above, but it still has to be sticking to that asymptote tightly because it approaches the asymptote. So, right, so now it's crossing the asymptote. So it's coming down into the area below the asymptote. And then once it gets to negative 1 on the x-axis, it's going to cross the x-axis because you can see you have 0 right there. So it's going to cross the x-axis and it's going to come down into negative region. And then its only other choice is to go down until it hits that y-intercept, go through the y-intercept, and it may go down even further to the right of the y-axis. We don't know, but we're not really drawing an exact sketch. We could pick a couple more points if we wanted to see what else it does between 0 and 2.2, but it's hanging out down there below the x-axis, and then at some point it's got to come back up because it's got to cross the x-axis again at x equals 5/2. So it's got to come up and it's got to cross that x-axis, and then it's going to just approach the horizontal asymptote as it goes to infinity because it can't cross it again. Okay, so example 11, you have h of x is equal to 2x squared plus 9x plus 4 over x plus 3. And so we're going to start out by finding the y-intercept. So 4/3 is where this function crosses the y-axis. And now we're going to find the x-intercept. So x could be negative 1/2 or negative 4. So those are the x-intercepts right there. All right, now we want to see if we have a vertical asymptote, which we do because the denominator would equal 0 when x is equal to negative 3. So that is our vertical asymptote right there. And then our horizontal asymptote, we have to look at our degrees of our functions in the numerator and denominator. And so you can see that the degree of the numerator is higher than the degree of the denominator, which means that the numerator is going to dominate. It's just going to get bigger and bigger and bigger, and the denominator doesn't even matter anymore. So nothing is going to stop this function from just growing as big as it wants to go. So there is no horizontal asymptote. Nothing's going to stop that function. Horizontal asymptote? No. Slant asymptote? Yes, because the degree of the numerator is 2, the degree of the denominator is 1, and that is a situation where you would have a slant asymptote. So to figure out what that slant asymptote is, you divide x plus 3 into the numerator, 2x squared plus 9x plus 4. So x goes into 2x squared, 2x times, multiply 2x squared plus 6x, subtract 3x plus 4. X goes into 3x 3 times, and that's 3x plus 9. And the remainder does not matter. It's just the main quotient that we need to know for our slant asymptote. So y equals 2x plus 3 is our slant asymptote. And if we graph a couple of points on there, we can draw that line. The question is, does the graph cross the slant asymptote? Because a graph can cross a slant asymptote, so we need to check on that. The way we do that is to see if the function can equal 2x plus 3. So we would use our cross products, and that is going to be 2x squared plus 3x plus 6x plus 9 is equal to 2x squared plus 9x plus 4. The x's are going to cancel, and you're going to end up with 9 equals 4. So no, the function will not cross the slant asymptote. Does not cross. Because 9 equals 4 is not true. So that's trying to tell me, no, it cannot equal that. So it can't cross that asymptote. All right, so now we just need to figure out where do we put the curves or curve. We don't need to worry about symmetry. There's absolutely no way I can imagine that this thing could be symmetric about anything because of where the asymptotes are. So we need to figure out where this curve goes. The first thing that happens on the x-axis is that there's this 0 at -4. And so we need to know, does the function start above that and go below the x-axis, or does it start below the x-axis and go above? Well, there's really no way it could start above and then as it moves to the right, go below, because the slant asymptote, it has to be approaching the slant asymptote, and there's no way it could be approaching either asymptote if it's coming in from -infinity like this. It's not near either one of them. So it would have to come in from -infinity like this, so that it's going to be approaching the asymptotes. So that there's only one way that can happen. And then we might think, well, is there a curve up here in this area? Well, it has to be approaching the asymptotes. And to do that in that region, it would have to be approaching up there and then come down and go up like that. But it can't cross the x-axis here because there's no zeros there. So there's not going to be a curve up in there. And you could check a point if you wanted to. You could check -2 as a value for the function and try that and see what happens. So if we put h of -2, we're going to have 2 times 4 is 8 plus -18 plus 4 over -2 plus 3. And that's going to be -6 over 1. So -6, -2, -6 is down there. So it's not going to be up there in that V shape. It's going to be down here where it will, as it goes from left to right, it will be approaching that vertical asymptote from the right side, and then it will approach the slant asymptote as it goes through the 0 at -1/2 and goes through the y-intercept and then continues to go up. So we don't necessarily need to check every interval. We can just think about it as you're going along the x-axis. What is this going to be doing? Is there a curve inside those V shapes? And all you have to do is check to see that there are no points in those V shapes between x equals -4 and -3, anything like that. There just isn't. So it's going to look like this. Okay, so here is an application for this kind of rational function. So they tell us some information first. A linear model of the cost for a business to manufacture X items is C of X equals MX plus B, where M is the variable cost to produce an individual item, and B is the fixed cost. Fixed costs are things like rent for your company's space or phone bill. Those are the kinds of costs that doesn't matter how many items you make, you're still going to have to pay those costs. And then the costs that are affected by how many items you make, those are your variable costs. So this next part is new. The average cost per item manufactured is the sum of all the costs. So all the things, variable costs and fixed costs divided by the total number of items produced. So this is the average cost per item. So now you're thinking of another number where you want to include all the costs, the fixed costs, the variable costs, your phone bill, everything, and then divide that by how many items you actually made after paying all that money for all those things to kind of get an idea of, well, it really costs us this much to make one item. So a cleaning service cleans homes. For each house call, the cost to the company is approximately $40 for cleaning supplies, gasoline, and labor. The business also has fixed monthly costs of $300 from phone service, advertising, and depreciation of vehicles. So they're giving us the fixed costs, the variable costs, and we're supposed to write a function, C of X, for X house calls per month. How much is it going to cost them to make X house calls per month? So C of X is going to be variable costs. So the cost per house call is $40. So 40 times the number of house calls, X, plus the fixed costs, which would be $300 per month. So this is the function that describes the cost of doing business for a month selling X items. Part B says write the average cost function that represents the average cost, C bar of X, in dollars for X house calls per month. So now we're supposed to write this function, which is basically just the cost function divided by the number of house calls. So C bar of X, which is just equal to C of X, which is 40X plus 300 over X. So now we're just going to find some values of C bar of X. So we're going to find C bar of 5, and that is going to be 40 times 5 plus 300 over 5. And so that is going to be 200 plus 300 is 500. So over 5 is $100. So if X is 5, you make 5 calls. It's as if you're paying $100 per house call instead of just 40. You're having to think of it as spending 60 more to make up for that $300 fixed cost. If you make 20 house calls in the month, that is going to be 40 times 20 plus 300 over 20. And if you add all that up, you've got 800 plus 300 is 1100 over 20 is going to be $55 per house call is what that is going to look like. So it's getting spread out over more house calls now. So C of 30, C bar of 30, that's going to be 40 times 30 plus 300 over 30. And so that's going to be 1500 over 30, which is going to be about 50. So now the more you spread out that $300 you're having to pay over more house calls, now it's really only $10 more per house call if you think about it that way. If you crank it up to 100 house calls in a month, and now you're down to looking like $43 per house call. So the cleaning service can realistically make a maximum of 160 calls per month. However, if the number of calls were unlimited, what value would the average cost approach? What does this mean in the context of the problem? So you've got your C bar of X is equal to 40X plus 300 over X. And this is a rational function. And you can see that the value of the function, as X gets very large, the numerator and denominator are both linear. They both have a degree of 1. And so the 300, as X gets very large, the 300 becomes insignificant. And so you have 40X over X. And so the value of that function, in other words, the horizontal asymptote, is at $40, which is the cost of a house call without thinking about the $300 of fixed costs. And so that's what this function explains, is that the more house calls you make, the less that $300 of fixed cost is going to be significant anymore. So if you could make an infinite number of house calls, that $300 fixed cost would just be unimportant. So your average cost per house call is going down toward just the cost of those supplies as you make more house calls.